The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees.
Thank you very much. It's a little past my bedtime, so I may move along here fairly rapidly. But certainly Federal Highway is interested in the alternative materials for a variety of reasons. And I've heard the word challenge used quite a bit with the previous speakers. And I think one of the challenges that Larry identified, that we've got a lot of civil engineers that work for highway agencies, and we need to get more material science and chemical engineers and people with chemical backgrounds so that they can understand these materials. How many highway agencies do we have here? Not many. That's another challenge, is getting the highway agencies to meetings like this. We used to have a lot more agencies attend these meetings, and certainly that has been a challenge. This is just kind of an overview of the topic that we're talking about. Certainly, alternative cementitious materials is a developing technology. Specifications and design codes, of course, are based on ordinary Portland cement as the primary binder. We need to address specifying, testing, and performance of these ACMs and to develop state-of-the-art methods to make sure we're building with quality. What properties are used to evaluate ACM performance? Well, there's already been some discussion of that. And I think we're going to have to adapt our test methods and to look more toward performance rather than prescription. And we're going to have to develop these special testing requirements for the materials. The objectives, key factors are sustainability and transportation. This is certainly a topic that's being discussed quite a bit. Not only the sustainability of constructing the pavements and the structures, but also operating the pavements and structures, and how long are they going to last? Do they affect other sustainability functions within society as well? Carbon dioxide footprint, very important, along with long-term durability in all types of weather and climate that we see in the highway system. Performance specifications and test methods need to be adapted for both cement and for concrete. For the range of new cements, we need to have quality assurance tests for the cement itself. A state DOT is not going to just assume that the powder they're getting in the bin at the concrete plant is going to meet the criteria of building a quality structure. They're going to need to have some sort of target chemistry, fineness, properties, that sort of thing, that they can check ahead of time that they are getting the material that they had contracted to receive. Concrete made with ACMs need to meet both material and structural properties. We want them to be durable, but they also need to be predictable in terms of their structural performance, their volume, stability, as well as their stress strain and fatigue capabilities as well. And using these materials must be seen as an advancement or certainly a viable alternative to Portland cement. If we have to go through a lot of special tests and a lot of trouble to use them, then I don't think highway engineers are going to want to use them. Do we modify the tests and specifications, or is a whole new paradigm needed in qualifying these materials? How do we verify that we're building with quality? Many questions will be asked, such as compatibility with ordinary Portland cement. In many cases, we may be using this in contact with ordinary Portland cement. How is it going to perform? Are there constraints on what aggregates we can use, on how they are cast and the setting properties, as well as volume change and cracking tendencies? Structural and corrosion properties with reinforcement are also very important, as been addressed already. Just a little background on Federal Highway has an exploratory advanced research program, and the project that Kim is working on is one of those projects. the project with Georgia Tech. We have a project with UCLA and NIST on SCMs and ACMs. We also have a project that's nearing completion with Princeton and NIST on ordinary Portland cement hydration and the nanochemistry and how this can be applied to models of hydration. And some of this, if that can be successful, then maybe we can move ahead and model some of the ACMs in like manner. We recently had a workshop on ACMs and alkali silica reaction at Turner Fairbank Highway Research Center, and we think that was very successful. A lot of good conversation back and forth. We also, as a federal laboratory, have the capability of doing cooperative agreements called CRADAs, where we can actually work with an industrial developer and sort of see how the technology fits in with the highway industry. And we have 2 cooperative agreements that we work with Ceratec in one case and Solidia in another case. And we weren't trying to develop the particular product. We're just trying to see how it fits in with the highway industry. Is it something we should consider? In both of these cases, we were using 3/4 inch maximum size aggregate and air-entrained concrete and making concrete that had typical or even better strength properties. And I'll show you a couple slides. We were doing freeze-thaw durability. So we're looking for comparable performance to typical highway concrete, something that looks like the concrete that we're used to using and performs reasonably the same. With respect to cement quality, we need to demonstrate that we're going to get the strength. There needs to be some sort of consistency in the chemistry of the cement from batch to batch. I assume in most cases we're talking about a powdered cementitious material, so we're going to have to measure its fineness and the rheology when you mix it with water and whatever admixtures you're going to need. And certainly time of set, workability period is important, volume change, durability, resistance to aggressive solutions. Things like sulfates, de-icers, very important. Are they going to hold up over time in the presence of all the various chemicals that we're using for de-icing of highways and bridges? Things like acids and alkalis and temperature extremes and abrasion, of course. Some states are still using studded tires, and if we don't have the abrasion resistance, then that's a potential problem. Maybe some of these will be better at resisting studded tire wear. On the concrete quality, we need to demonstrate for the particular project with a mixture that is going to be used, that you're going to get strength. Can you pump this material and place it if necessary? Air void properties. So far, most of what we're looking at, we're using air entrainment. Now, there may be some alternative cements that will have sufficient durability without needing air entrainment. That would need to be a factor to be considered. This slide just sort of reviews the current situation where most concrete and infrastructure in the U.S. and Canada probably is ordinary Portland cement, but we are using quite a bit of the various different supplementary cementitious materials. Quite a bit of Class C and Class F fly ash. Many agencies are going to higher amounts of fly ash. We're also discovering that the fly ash supply is changing. What fly ashes were available in some cases are not available anymore, and you may have to go somewhere else to get them. So to some extent, agencies are switching around to different materials that they're using, and this is somewhat of a challenge. Slag cement is being used quite a bit, silica fume to some extent. There's more and more interest in natural pozzolans, particularly as fly ash may not be available in certain areas, then natural pozzolan may be a substitute for the fly ash, particularly in alkali silica reaction mitigation. Some state agencies are routinely using ternary blends as well. This just kind of reviews the different cement specifications. To a large extent, for the typical cements that we're used to using, AASHTO and ASTM have harmonized so that they're pretty much the same specification. But ASTM does have the performance blended cement, the C1157, the expansive cement specification, and then the rapid hardening performance specification. Those might be used for some of these ACMs since they're based mainly on performance criteria. These are the specifications for supplementary cementitious materials, which, as was discussed, we're trying to use more and more of these materials. In terms of the research that we're doing at the Turner Fairbank Highway Research Center, we are taking a look at higher fly ash content. We're working with NIST on using more ground limestone with Portland cement. We're looking at rheology of pastes and mortars with these different materials, characterizing and optimizing fly ash. We have the capability of looking at the calorimetry and the kinetics. And there is some previous work that was done by Peter Taylor on the compatibility of cementitious materials with admixtures, which addresses various tests that might be used to look at particular cements with particular admixtures as well. With respect to our exploratory advanced research program, the high volume fly ash studies were done with Purdue and Auburn universities. Also NIST and NRMCA were involved. We did some work with cementitious composites with carbon tubes with Texas A&M, hydration modeling with NIST and Princeton, and also Federal Highway helped support the Hydration Research Roadmap, which is a NIST publication, and there is one chapter in that publication on alternative cements. That's just a picture of the publication. There was a transportation pooled fund study that just wrapped up, which concentrated on ternary mixtures or various blends of cement and different supplementary cementitious materials. And the reports on that are in the process of being published. With respect to alternative cementitious materials, we do have a federal agency steering committee which is occasionally met. There are other agencies that are interested in these materials, particularly the Corps of Engineers and NIST and the Department of Energy for some of the nuclear research as well. And as I mentioned, we do have these cooperative research and development agreements. With respect to those CRADAs, the conditions are that, we as the government are not directly endorsing or promoting these particular materials, but we're working with the developers of the technology to see if they would fit into the type of materials engineering that we use in the highway industry. I'm not going to get into any detail on exactly what the technologies are. Both Solidia and Ceratec on their websites have white papers and that sort of thing that describe the technology. Solidia basically is a cement that carbonates rather than hydrates, and Ceratec is a system where you have a hydraulic Class C fly ash where the hydration of that material is controlled, and you get basically similar properties to Portland cement concrete. With Solidia, we recently completed some freezing and thawing tests, again with our 3/4 inch maximum size aggregate air and train concrete. I think that was 540 cycles of freezing and thawing. And in general, the material's holding up very well. We're getting a little bit of scaling, which is not a surprise. We also were doing some intersections and sidewalk work at Turner Fairbank Highway Research Center, and some of the Solidia paver block were used in part of that sidewalk. So we're trying to get the material out there, see how it performs in actual practice. Some of the specimens that we have on hand for future testing, and an example of a flexural specimen that was already broken. With Ceratec, we've done freezing and thawing work with it. We actually mixed two batches in two different mixers, basically the same material. One was in a high-energy vertical shaft mixer, and the other was in an ordinary drum mixer. And the freezing and thawing durability results are pretty good on both, and again, a little bit of scaling. But it's interesting to note that the spacing factor with the high-energy mixer is about half of that of the drum mixer. So we were making smaller air bubbles with that high-energy mixer. With the Ceratec, it has been used in various industrial and transportation applications. This is just an example of the Port of Savannah. I went down and observed a project where they were doing paving. They were replacing the rutted asphalt pavement for these heavy cranes used to move the containers around in the port. And this shows the concrete actually in use in that particular case. I also observed a placement by pump with the Ceratec material, the 100% fly ash-based cement in Galveston at a molten sulfur facility. And in general, the concrete, it looked a little bit different maybe, but it went through the pump and was placed in a reinforced concrete wall with no apparent problems. Our structural lab has started to do some structural properties on some of these concretes. Unfortunately, they've had a bit of an interruption, and hopefully they can get back to it in about 2 months. But they developed some plans for looking at structural properties in addition to mixed proportions and basic properties, to take a look at bond reinforcement, stress block parameters, creep and shrinkage testing, and full-scale testing of structural elements would be down the road, and hopefully we would have a chance to do that. This is just some preliminary results with the high fly ash concrete, where we took a look at splitting tensile strength in relation to compressive strength and elastic modulus in relation to compressive strength. Also did some initial pull-out bond to pre-stress strand tests using a modified ASTM C1081 test, and preliminary results on a Ryland test on bond to rebar. And this just shows some of the preliminary test results. Unfortunately, we just have begun to get involved in this or into this and getting a little data, but have not been able to continue it at the present time. So that basically is what Federal Highway is doing, and the chair had asked for some potential discussion topics, so I put on this last slide just an example of some of the topics if we wanted to discuss.